Now we'll talk about Bohr. And Bohr's name was this, Niels, with an S on the end. I'm not sure what. He might be, I forget. I think he might be not Norwegian, maybe Norwegian. What were all those countries up there? Not that Norway is one of them. Sweden, Finland, Denmark. I think he might be from all those, but I really forget. What? Because have you noticed that like baby names change too? Have you noticed that like the things that people are naming their babies nowadays are not what like you guys were named? It's because names come in cycles like that. So like have you noticed that like some of the names that are popular now like were popular back when your grandparents were small? Right. Right. That's why. All right. So his experiment is called the quantum theory.
Is that where quantum physics comes in?
Yeah. So this is where the water between physics and chemistry get kind of muddy. Okay? And this is where we also start to get into some pretty complicated mathematics that we will not learn in this class. In order to really, really understand quantum theory, you have to understand a heck of a lot of math that's way above where you guys are right now, like calculus and higher than calculus. So the big important thing that I want you just to know here, and we're going to, I'm not sure that he actually I guess he did. He did this test that was called the flame test, which we will do. This is a pretty cool lab, actually. Okay. He, of course, was doing way more complicated thing with the results from the lab than we will do, but we will do like the visual, like the easy visual conception version of the lab. Okay. And so the really important thing here is that energy gets transferred in what we call specific, and then we use this word discrete, okay, amounts. Not in what we call fractional amounts. Okay? So, for example, I'll let you finish writing there. Yeah, discrete. That's a good word, right? It's a D. Somebody ask Siri real quick. What does the word discrete mean? What? No, discrete. discreet. What does discrete mean? Carefully and respect one's speech or actions, especially in order causing events to gain advantage. So like really like specific, right? Intentionally what? Unobtrusive means like, right. So this is where maybe like in the mathematical definition of discrete is just a little bit different than the sort of English version of discrete. In English, it mostly means like almost secretive and like calmly, quietly. But in math, it means calmly, quietly because it's in a certain block of an amount. All right. So here's a little graph for you. Okay. 1 unit of energy, 2 units of energy. Okay. So you can transfer this quantity of energy right here, 1 unit, right? Or you can transfer 2 units of energy. But there is no possible way to transfer a half or 1.5. Does that make sense? No matter what you do, energy will always be transferred in these specific increments, either 1 unit or 2 units, but not 1.5, not 1.75, not 0.11, always in whole units. Does that make sense? Ellie, Cassandra, you guys with me? Yes. That's kind of how that goes. Does that make sense now? Shake your head. Does those sentences make sense? Yes. Do you see how this is going to get really, really complicated if I try to explain it to you any further than that? Yeah. Okay. So here's the important things of his theory as it pertains to us here in introductory chemistry class. Okay, there's these things. They're called energy levels. Okay? And these are the pathways electrons follow. Okay? So it's not just this chaos idea of where the electrons go in an atom. They have specific places where they're supposed to go. Make sense? The other thing is that electrons do something called emit. And emit means give off. I should put this in parentheses probably. Okay? Something called a photon. And a photon is light. When they jump down a level. Okay? So like I said, they're in these different levels, these pathways, these energy levels, and they can jump from one level to the other. But if they jump from a higher energy level to a lower energy level, then they're going to give off a photon and they're going to make some light. Make sense? Okay, don't try to think too hard about it or you'll probably just crash your brain. Just trust me. And then the third thing that I'm just going to kind of put here is that there was some other things in his theory that were really complicated. It related to what we call quantum mechanics. But I just want you to know that the simplified version of what he said is way enough for us to learn here in this class, but that he had lots more to his theory. Okay? I remember, so my grandfather was a nuclear physicist. Yeah? So my grandfather was old enough that he actually worked in the Manhattan Project during World War II. Do you know what that was? It's the program where they invented the nuke that eventually got dropped on Hiroshima. Right. And because basically all the people that were in his kind of career were employed for that project during that time of history because they were trying to make this happen, right? And so anyway, I just remember like in his later years, this would have been, I don't remember what year this was, but it would have been like maybe like 10, 15-ish years ago, not that long ago. I remember visiting him and him like talking in great detail about this new discovery that had just been made called the Higgs boson particle, I think. But it was like a subparticle, like a part of a proton or something. I can't remember. But I remember him talking about that, just like being really excited about it because it was part of this really complicated mechanics stuff that physicists for years had known something had to be there and they hadn't been able to find it. And then finally somebody found it. Kind of cool, right? That stuff exists, okay? All right, so here's his idea. There's the nucleus. And then there's specific places where electrons travel. We often depict them as circles, okay? They're not really actually mostly circles. They actually have kind of some different shapes. But circles is plenty good for you to think about it in terms of this class. All right. And then, so we talked about this. So his model sometimes gets called the planetary model. Can you see why? It looks like the solar system, right? But can you see like the connection there? Like it's not that different really, right? Except for the chaos idea. So the other idea that often this one gets called is the orbital shells idea. That's two L's. Okay? And the shells is another name for where the electrons go. Does that make sense? So like I called them levels up here, right? Another name for it is shells, but they really mean the same thing. Sound good? All right. What's still important today from Bohr's theory?
Well, there's none left. There's none left on our list that we used today.
Yes, almost everything from this theory is still important today. There's some details that have been changed since. There's another guy who came along with a theory. His name was Schrodinger, and he had some more complicated stuff. Quantum mechanics has continued to be studied more and more and more and had more discoveries. But the basic gist of what Bohr discovered, we pretty much use it still today. Sound good? Cool? All right. Last thing I want to add to this notes is a little bit about a model. What is a model? What's a model car?
Like an idea of it. It's not for like a drawing of it. But no, not a drawing, but
A little version, right?
Yeah, that type of version.
Yeah. So here's what I want you to realize this about you guys. Okay? We just talked about all of these different models, right? We talked about the orbital shells model. We talked about the central nucleus or electron cloud model. We talked about all these different ones, right? But what I want you to know is that any model is not something so simple as a photograph. It's not just perfect representation of what we're trying to learn. Okay? Instead, it is an idea, okay? And it helps us understand the world. Okay? As an example, there are a lot of mathematical and conceptual models right now about how we understand the COVID virus, right? A lot of different people have different ideas. There's a certain amount of consensus about certain aspects of it, but there's some disagreements about other aspects of it, right? And the reason is because when you're studying science, stuff changes. When does it change? Does the actual way that things are working change?
No, just the way people think about it.
No. What changes, it changes when you have more time to learn, right? More experiments, right? Those things change. The virus has changed a certain amount because of like mutations and stuff, right? But the basic gist of the virus probably hasn't changed as much as our understanding of it has changed because we've learned more stuff. Do you see how that's going here? And so the history of the atom is the exact same way. There's been a lot of different discoveries over the course of history, and we talked about the really big ones, right? Can you imagine that there was probably some other experiments along the way that people thought about? Of course there were. These are the ones that we talk about the most because they've made the biggest effect on the way that we understand the world. But any model is not just a simple, real explanation of how things work. It's just a collection of all the best information that we have. And because of that, it will never be complete. Does that make sense? Think about how long democratization idea went. How many people along that way probably thought, well, this is how it is, this is how it is, this is how it's always going to be, right? But lo and behold, it changed.